This is the last bit looking at RStudio and R Markdown, and I'm going to explain one of my favorite tricks of just obtaining or visualizing uncertainty. And once you understand it, I think it is going to be very useful for many contexts. So if I look at MP, which was the basic Poisson model, and maybe look at the summary. Summary MP. So what we are usually looking at in a summary, what is the estimate, which way it goes, is it significant, which means if you imagine a normal distribution with mean of the estimate and standard error, which is the standard deviation of that normal distribution, whether the distribution or the whatever percentile of it overlaps 0 or not. And this is what this star 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 captures, that it's very far from 0, or the uncertainty is really narrow. So it might, the actual number might be close to 0, but the uncertainty is even smaller, so the distribution is not crossing 0. That's what this p-value means, and that is really calculated based on assuming this normal distribution and the ratio of the estimate and the standard error. Now, we have more information than this. How many of you have ever used coefficient of MD? P, sorry. I'm pretty sure most of you have used this before. How many of you have used VCOV MP? Sometimes. You know what it means, I'm pretty sure. You're familiar with variance covariance matrix. Is something that we estimate alongside of the coefficients that is coming out of the optimization that is happening in the background. And this is really the two really key information that we want to store other than the log likelihood and metrics like that. And so if you take the diagonal of this, which is the variance, and you take the square root of that, that's exactly your standard error. And now if you want to take this standard error and capture that uncertainty around the intercept and the slope, what kind of shape you would get? You would have this kind of standard error around the intercept and this kind of standard error around the slope. So you would get this, right? But you also have this correlation, which is very small, but that is also really a covariance. So if you get rid of the variation component, the correlation might be still significant. You see, this is tiny, tiny number. Compared to that, you have this covariance. And so the true relationship is often like this. So it's not like this. So by ignoring the correlation that is also happened to be available, you are overestimating the uncertainty. And there are functions to give you, okay, this is what kind of error you get in a ggplot, but how do you get that if you need it? And there is no easy way to get it. And this is a really high conceptual level thing that once you understand, and that asymptotically we estimate these as assuming this normal distribution around the parameters, and how they correlate is kind of, you look at it in a multivariate space, and that's where the correlation is coming from. So we have all this information, and now you can capture this from the removal sampling model, from the Poisson model, from the distance sampling model, any kind of model where you have the estimate and the variance covariance matrix. And the theory says that these two capture a multivariate normal distribution with mean vector, the coefficient, and variance covariance matrix VCOV. So really, we can generate thousands of millions of pairs of coefficients coming from this distribution, which on average is going to be minus 1.7 and 2.3, but you would then see the right amount of uncertainty around those predictions if you take each of these. And now I'm going to walk you through the steps. So if you plot the line, intercept and slope, you get this. And now we're going to plot maybe thousands of lines, and what those cover is going to give us the uncertainty. So load the mass package that has something we will need, and say, let's just do 100 iterations. We won't have time for more. And then we have this model matrix, and we get the coefficient from the removal modeling and the variance covariance matrix. So it's the same as for the Poisson case, same functions, but it now has the estimates we obtained for our bird, and a similar interpretation when it comes to estimating these and using these to talk about the uncertainty. So what I do next, this is the crucial step. I'm using multivariate normal distribution, and I want to generate B100 random numbers from this multivariate normal distribution with mean CF and VCF as the variance covariance matrix. So this is what it looks like. 100 realizations from the same distribution. If I look at summary, then you can look at the mean, and that is going to be very close to this one, because that's the mean of the normal distribution. If you calculate the standard deviation for the two columns, that is going to be the standard error, what you would get from the diagonals. So that's how we calculate this, but there is also the right amount of correlation between the two. So if I plot it, then I see when the intercept is increasing, the slope is going down. So there's this negative correlation that we would expect based on this. We do the same for the distance sampling model.
Peter?
Yes?
This is blowing my mind.
Okay, maybe then what I should do is not explain it too much, just if you ever need to propagate the error, look at this code and ask me questions. But we need this error somehow to get entered into the GLM. So what I'm
in a good way. Please don't stop. I mean, I'm very excited. Yeah, it's a bivariate normal though, because you have two coefficients being estimated, or I'm completely missing it.
This is normal in the sense of the asymptotics of maximum likelihood estimators, and not in the sense of our data. This is about the parameter space. And so that is what the confidence intervals are going to capture, and we want to take that uncertainty and represent it in the offsets. So instead of just one value, we want to create a distribution of those values. So when you repeat the Poisson GLM using like Bootstrap, then every time you take a new subset and fit the same model, you might use a slightly different offset. And that's how you get this uncertainty into the Poisson model. Otherwise, your offsets are fixed. Because we are fitting these in independent steps, how do we take the variation from one component and pass it into the next one? This is what we are trying to achieve here. So if we run this code, then we are going to get 100 values Oh, I missed this line.
And
We have the
where's
components.
The multivariate nature coming from?
Which one?
The multivariate nature of it, where is it coming from? Is that what is not?
Okay, summary MP. You have two variables. That makes it bivariate. If you have four variables, like four coefficients, that makes it four-dimensional. And we have the same kind of setup for summary M distance sampling. Here we have three. So coef M dis is length of 3, variance covariance 3 by 3. And so this captures that multivariate relationship that we estimate. So that has nothing to do with our data. The data can be Poisson, multinomial, but at the end, using this maximum likelihood, so we describe the likelihood, maximize it, get an estimate, and that maximum has a curvature. It can be flat or it can be really pronounced. That's what the standard error relates to when we do the maximization, and that's captured in this variance covariance matrix. And we are trying to use this uncertainty. Is it like sharp or flat? If it's flat, then our offsets should be more variable. If it's really sharp, then our offsets might be just really almost like a constant. And if we are uncertain about the estimate of phi or tau, we should somehow incorporate that uncertainty into our offsets so that it is also going to be part of the uncertainty we get for our density estimate. So once we have captured this uncertainty through this multivariate random number step, which if it's still a bit fuzzy, maybe that's okay, but you can still repeat this step. And at the end, instead of a single offset, we get 100 offsets. So OB, now instead of just one column, it is 100 column. So for each of those fixed offset, now we have a range of values, which together represent this uncertainty. So the histogram of OB row 1 is like this. So somewhere here, this is what we get as our offset when we just give it as a single number. But really, instead of 0.16, it can be 0.12 or 0.20, sometimes less often. Mostly it's around here. So this is the uncertainty we want to pass on into the GLM. So next, we, in a loop, fit 100 GLMs by resampling rows of the same data set. This is what Bootstrap does. You take the same amount of rows and resample with replacement. So we take that subset from the response, from the data, and from the offset. So this is without propagating the error, because we are just using our plain old offset from before. So apart from the resampling, nothing else happens. This is just a fixed value. Now here, for number 2, we have the same resampling, but now we are looking at this OB, which is, now we have 100 columns. So we take the resampling, like rows according to this sample, and column I, because that's the next realization of the offset under the uncertain models that we've created before. So that is going to be Bootstrap run number 1, 0.14, Bootstrap run number 2, 0.17, and so on. Going to be more in here, sometimes out here. And as a result, our Poisson coefficients are going to be more variable than with a fixed offset. And if I run this and look at the standard deviations, I'm going to see hopefully some difference. So right now we are only saving the coefficients. So now instead of just one estimate and some standard error, we are doing bootstrap. So we have bootstrap-based standard errors. And we expect that number 2 should have higher standard errors because we have that extra variability passed through the offsets. And so when the offset is fixed, we have these standard errors, 0.048. Now for the intercept, we have 0.053. So it's quite a bit larger. For the deciduous coefficient, 0.063, 0.064, not a lot of difference. And we know offset is going to influence the intercept more. So that's why you see the error coming from the intercept. And now we're done. This is how, this is one way of propagating this error. And you can also look at confidence intervals when you make the prediction. So here I'm just looking at very few actual prediction values along the range of this coniferous forest. So I think this is like 0 and the last one is 1. So you see yes, so when there is no error propagated, then this is the confidence interval you would get around the predictions for deciduous equals 0. And this is when you propagate the error. You see, this is wider, 0.19, 0.20. Here, 1.57, 1.72, 1.46, which is smaller than this one. This is higher. Actually, no, the other way around. So it's a bit shifted. But we also just used 100 iterations, so you could use 200 or more to kind of smooth it out a bit. And because we are kind of short on time, you can follow up with me if you need to understand this better, because down the road, you want to use it. Otherwise, I wouldn't take up more time than this. So maybe I'll just jump back to the slides, spend a few more minutes on giving you the highlights from there, and then we can open up for discussion.